the previous class we were discussing about the use of operation amplifier, and then I was explaining you what is a linear voltage regulator, how to obtain a regulated output voltage from unregulated voltage. In that connection we discussed about how to design a transformer, then how to design a heat sink, and then also I explained in detail how the regulator is working. So, so far this is good. Now, there is one more aspect we have to discuss in the voltage regulator, that is how to give a short circuit protection, because the short circuit protection will be used in analog circuit at very many places, not only in the voltage regulator, even at other places that you will see as we proceed. So, we will discuss now about how to provide a short circuit protection. So, our topic today is short circuit protection. Now, let us see our circuit that we have discussed so far, the regulator circuit. That is, we have the input AC, and then we had this through this step down transformer we are rectified that into DC, then the unregulated DC is obtained here, and that is regulated through the use of transistor, series pass transistor this is called. Then you have the output voltage, that whatever is here, that is fed back to the, we had this operation amplifier. So, the operation amplifier we had given the output, and then this point is given a feedback. So, this is the regulator circuit that we have seen so far. So, essentially you give a unregulated voltage at this point and get a regulated voltage at this point, and this is the reference voltage and this is the feedback point. Now, we can get whatever voltage we want. For example, if this is 5 volt here, and if I put here R and here R, say 10K, then I will get 10 volt regulated. This is what we have discussed so far, and then of course, I also told you that we had to have one small large capacitor to be connected at this point to ground. This is to avoid oscillations. So, this is normally alternating capacitor, and then the load is connected here. This is the load. Now, in this circuit, suppose if I connect a load, say 10 volt is here, and if I connect 10 ohms, then 1 ampere current will be flowing here. So, you will have 1 ampere current coming, and that 1 ampere current will be flowing through this transistor, and then it will flowing through this. Suppose if the output voltage is 10 volt and if the input here is say 20 volt, because it has to be more than 10. Now, if this is 20 volt and if this is 10 volt, then you have 10 volt across this transistor, the series pass transistor will have 10 volt, and the other 10 volt is here. Now, if load is 1 ampere current, then 1 ampere current flows through this, and then 10 volt is present across this transistor. Then the power dissipation on this transistor is 20 minus 10, that is the voltage divided into 1 ampere, that will be 10 watts. So, there is a 10 watts of power dissipation, and we had shown last time that how to design a heat sink, so that junction temperature is kept within the limit. Now, what happens if I short circuit the load? Suppose if the load short circuit means instead of 10 ohms I put a 0 ohm, then obviously if supposed to be 10 volt, then infinite current have to go, or other way around, large current flows through this transistor. And then if this is 0, if this voltage is 0, and then if this is 20, then 20 volt across this, and enormous current flowing through this will heat up the transistor, and the transistor get destroyed immediately. So, if there is a short circuit, automatically this transistor goes bad. This is because if this is 0, this becomes 0, and this is 5, the immediately output of the op-amp goes very high, and then the output goes high, it tries to drives high current, and since this is 0 and I current is flowing through this, and you get enormously high wattage of dissipation here, and this transistor goes bad. So, we had to provide a short circuit protection in the sense that even if there is a short, the transistor should not go bad. So, what is that we can do for that? Now, that is done is you add on series resistance here. Now, if I add a series resistance across this, then whatever current that is flowing through this will develop a voltage across this. So, voltage across this is this R into the current what that is flowing through this. Now, to this what I do is I will add a transistor here, connect this, then connect the transistor here. Now, this transistor and there is this resistor and this transistor put together gives a short circuit protection, and even if we short this now, this transistor will not go bad and there will not be large power dissipation across this. That is achieved using this resistor and this transistor. Let us see that how this works. Now, as I said, the current that is flowing through this produces a voltage. If the voltage, this voltage, the voltage across the resistance is same as voltage across this base and emitter of this transistor. So, we know that base and emitter of the transistor voltage exceeds 0.6, there is a 0.6 voltage, then we can say the appreciable current is flowing in the collector. So, if more current flows through this, we know obviously there will be a more voltage drop, and if the voltage exceeds more than 0.6, that is then the base emitter voltage exceeds 0.6 and this transistor start conducting. So, current will be started flowing. So, that current essentially comes from here and through this, then it goes here to this point. Suppose if it is grounded, then the current actually goes through this. Now, the problem is that ordinarily suppose if I do not connect this, if the short circuit protection is not there, then this current is only the base current, and the base current is negligible. This current what is flowing is negligible current, that is the base current that is supposed to flow, and that is very small. So, normally very small current is flowing and there is no voltage drop across this resistance. So, there is no problem because of this resistance and the circuit works normally. However, when the short circuit occurs, then the current flows through this. Now, there is a current that is flowing through this, and there will be a current through this, and there will be a voltage drop because this current will be high, because if suppose if a large current flows and if this voltage start increasing here, then more current will be increasing. Now, the question is how much current it will flow, because this voltage cannot go more than 0.6, because if it goes 0.7, then enormously large current will flow through this and large current will flow here, and that will develop a large voltage across this, and that makes this voltage at this point less, because once short occurs, this op amp, this voltage goes 0 and this is already high and this puts high voltage. The high voltage is normally depends on what is the supply that is given to this. Normally the supply given to this is this. So, in this case it is 20 volt. So, once short occurs, this puts voltage at this point tends to 20, and then voltage at this point depends upon what is the current that is flowing through this and into this resistance. So, if there is a voltage drop across this, then this 20 will not appear as it is at this point. If there is a 10 volt drop, then here 20 volt, you will get only 10 volt here. But then if it is 10 volt, we know that this will be 9.4 and this will be 8.8, but then 8.8 and this point is 0, then the voltage difference so high that heavy current will go through this, and then further large voltage drop will occur. So, eventually what happens is this point will sit at 0.6, this will sit at 1.2, this will sit at 1.8. So, essentially in actual case this will go to 0.6, this will go to 1.2 volt, this will go to 1. This will go to this point will go to 1.8 volt. So, one short occurs. Okay, I had to connect this. So, voltage at this point goes to 1.8 volt and this sits at 0.8. So, if this is 20, then obviously depending upon this resistance the current flows. Assume that this I had put say 3.3 K, then 1.8 here and 20 volt here, that will give me about 18 volt, 18 by 3.3 K, around 6 milliampere current will flow through this. So, you will have 6 milliampere current is going through this, and this is sitting at 1.8, this is sitting at 0.6. So, now if you look at how much current that is flowing through this, now this is at 0.6, this is at 0, then the suppose if I put 1 ohm resistance here, then obviously to get 0.6 here, 0.6 ampere have to go through this. So, this is 0 volt and this is 0.6 and this 1 ohm. So, the current is flowing through this is only 0.6 ampere. That means even if I short circuit this, the current through this cannot be more than 0.6 ampere. So, the current is limited to 0.6 ampere, that is because of this resistance. So, eventually what really means is the I short circuit current is actually R current is actually R into IS. R into IS actually is given by 0.6, because 0.6 is what it can come, and that should be equal to R into IS. So, if I put R as 1 ohm, then 0.6 volt to come, then IS have to go to 0.6 amps. So, I can select R to get whatever current short circuit current that I required, because in the normal operation, then in the sense if I put for example 1 ohm, then even in the normal operation if the current goes more and if you get 0.6, then this start conducting and it will get into current limiting mode. So, if I put 1 ohm, then I can take only 0.6 ampere maximum in this case. Now, this is a celebrated short circuit protection because this is a foolproof arrangement, and as long as you have this, and if the transistor heat sink and the transistor rating is correctly selected, even if you short circuit, it never goes bad, because this acts very rapidly, and it is a celebrated short circuit protection. Everywhere it is used extensively, and it is a must for any voltage regulator. Otherwise, the invariably this transistor goes bad under short circuit condition. One can select the different values of resistance to get different amount of short circuit current. But there is one issue in this, this we call the normal short circuit protection. There is one difficulty even with this. Now, for example, if this is 20 volt, if I short circuit and I limited the current to 0.6 ampere by using 1 ohm here, in that case under short circuit condition you will have at this point 0.6 volt, at this point 20 volt, and then 0.6 ampere going through this. So, roughly you have 20 volt across this transistor and then 0.6 ampere going through that. So, voltage power loss across this will be 20 into 0.6, that is around 12 watt of heat dissipation will occur across this transistor. But then if you see the normal working case, when short circuit is not there, you will find that if 0.6 ampere is going, at that time this is around 10 volt is here, and around 10 volt here and 20 volt here, you have only 10 volt drop across this. So, 10 volt drop and then 0.6 ampere current is what is the normal condition. So, if we write like this, under normal condition, power dissipation actually is 20 minus 10 into 0.6, that is 10 into 6 watt. Under short circuit, power dissipation actually it comes full 20 into 0.6, that comes 12 watt. You see the point here that under short circuit, even though we are limited the current that is flowing through this, but power dissipation is large, and this can go extremely high, because if the voltage if the high current regulator is made, or the voltage is high. But more important is, we would have designed our heat sink for normal heat dissipation, that is for 6 watt. But now we find that under short circuit condition 12 watt is there, and if short circuit is left like that for long time, then this transistor dissipate 12 watt, and the junction temperature will go much higher than what was calculated, because we would have calculated the heat sink for only 6 watt, and we would have applied the heat sink for 6 watt, and correspondingly the junction temperature would have been lower. But now if it goes it dissipates 12 watt, the junction temperature can go high and the transistor can go bad. So to avoid this, what we can do is, we have to make a circuit such that the power dissipation is same even under normal condition, that is 6 watt, and even at short circuit condition this power dissipation should not go to 12 watt, it should be made 6 watt. Then the same heat sink what we have designed under normal working condition can be utilized, and even if short circuit is left for a long time, this transistor will not go bad. So it is essential. Otherwise, I had designed a heat sink for 12 watt, even though the normal condition the 6 watt it only dissipated in the transistor. But then designing a heat sink for 12 watt is a waste, because it will be very big and it is not necessary. One can make it such that under short circuit condition also only 6 watt heat is dissipated, and that is very much essential to reduce the cost and size of the unit. So how to change this, because we want to make sure that not only current limited, under short circuit condition only lower wattage of not full heat is dissipated, lower watt heat is dissipated. Now for doing that, what we have to do is, see normal current when short circuit is not there, I want 0.6 ampere have to go. When short occurs, I know more heat is dissipated. So one way of reducing the heat would be reduce the current limit. Do not limit at 0.6 ampere, you limit it much lower than 0.6. For example, when short occurs, I should make sure that the current limiting takes place as soon as 0.3 ampere flows through this. In that case 20 into 0.3 ampere will give me only 6 watt of dissipation. But as long as short is not there, when the output is a 10 volt, then this should not come into picture, the current limit should not come into picture up to 0.6 ampere. So that is to be achieved. That can be achieved by slightly modifying the circuit in the following manner. So we can do that by modifying the circuit. So what I do is, I will start the discussion from this capacitor. So we have a input capacitor here, and then we had this series pass transistors, and then we had our output resistance that I put it here. Then our output is here. This is our output point, and this is our load. Take this. So this is the feedback part. Now I put the regulator here. So that is to be biased, so that I can do this, then this, and we know this is grounded here, and then we give a supply to the op-amp like this. So now what I do is, I will connect the short circuit protection transistor, but not directly. I divide this voltage and operate this and connect the short circuit protection. Now this go as usual to this, and the base will be connected to this. Actually we had in the earlier case only this resistance and this transistor for short circuit protection. Now, we added these two resistors extra and terminated the base to the midpoint of this, and once you do this, we will soon see that this circuit gives me the protection in the sense that one short occurs, then the current is limited at lower current, that is in our earlier example the normal current was 0.6 ampere. Now, I want to limit this to 0.3 ampere. That work is done by this, and that happens because of this voltage divider. This is a remarkable circuit because one need not unnecessarily over design the heat sink for the regulator because of this arrangement. This is actually classically called fold back current limiting. This is called fold back current limiting. That idea is a normal current should be much higher and short circuit current should be much lower. That will make that heat dissipation on this transistor is same under short circuit condition as well as under regular work condition. Definitely the under short circuit condition this should not go higher than the regular thing. So, we can avoid designing a bigger heat sink. That is the idea of this. Now, the question is how it is working. Now, we will name this resistors, this is R, I will put this is R1 and this is R2. See, the working is not very complex because many people struggle a lot to understand how this is working, and then invariably in student community this is a tricky issue, and very often students come and ask me how it is working and so on. So, it is nothing difficult in it to understand. If you follow this carefully, you can understand quite easily. See, the basic concept is that the base and emitter voltage, if it exceeds more than 0.6, that will be conducting, and then current limiting will take place immediately. So, the question is when the voltage difference will be 0.6. Now, see under short circuit condition what happens. Under short circuit condition, this voltage becomes 0. That means current limiting will take place once this voltage goes to 0.6 volt, because this is under short circuit, this is 0 volt. So, obviously once it goes to 0.6, the current limiting should take place. So, when this will become 0.6, if this has to become 0.6, obviously this has to go more than 0.6, because whatever voltage is here, it is divided between these two, and that voltage only appearing here. That means this has to go more than 0.6. Assume that this goes to 1.2 volt. This goes to 1.2, only when it goes to 1.2 this comes to 0.6. That means I have to put equal resistance, then 1.2 comes, then this will go to 0.6. Suppose that means I need 1.2 volt drop across this. If it is 1 ohm, suppose if I put this as 1 ohm resistance, then 1.2 ampere current flows through this, you will get 1.2 volt here, that will give you 0.6, then the current limiting will take place at 1.2 ampere. Or I can also do like this, I want only 0.6, I can select not equal resistance here, I will not put equal resistance here and here, I put this value smaller, this value larger, such a way that this is not 1.2, I can get 0.6 when this is say 0.9, or I can make it even say at 0.7 volt. When it is 0.7, here I will get 0.6. All that required is I have to select these resistance. For example, if I put here 10K to get 0.7, what is the resistance value of R1 required? So, 0.7 into R2 divided by R1 plus R2 supposed to be 0.6 volt, because I wanted at 0.7 the current limiting should take place when short circuit occurs. That means I want limit the current at 0.7 ampere at short circuit current at short circuit. Now, in that case what is the if I take R2 as 10K, then I need 0.7 into 10K divided by R1 plus 10, that is equal to 0.6. Now, we can find out R1, the R1 roughly will come around 1K, because if you calculate this back you will get 0.7 volt at the top, and then down actually you will get this. So, if you redraw this one, that is 7 divided by R1 plus 10 becomes 0.6. So, we can write 7 equal to 0.6 R1 plus 6. So, that will give you 1 will be equal to 0.6 R1. So, that will give you R1 will be equal to 1 divided by 0.6, that is in kilo ohms, because we have taken everything in kilo ohms. So, 0.6 R1. So, R1 will be 1 by 0.6, that will be 1000 divided by if I take in ohms. So, that will if I multiply by kilo ohms, so that becomes 1000, and that becomes 600. So, that actually gives you roughly 0.5 K. So, you will get R1 actually comes out to be around 0.5 we find that if I put 10K here, and then roughly R1 comes to be around 0.5 kilo ohm at this point. So, if I put 0.5 K here, then 0.7 volt here, 0.7 volt here will give me 0.6 here, and that will limit the current. That means, under short circuit condition, when 0.7 ampere is flowing through this, you will get 0.7 here, and then 0.6 volt here, and the current limiting will take place at that time. That means, at 0.7 ampere current limiting will be taking place. But then see, under normal working condition, that is when it is not shorted, then you will have at this point 10 volt. So, at this is not going to be 0 volt, and normal condition this is going to be 10 volt. So, if this is 10 volt, and if I want current limiting to take place, this point I have to go to this point I have to go to 10.6. Only when this goes 10.6, current limiting will take place, because this is 10. So, this only when it goes 10.6 current limit will take place. If you have to go to 10.6, this has to go, if this point I have to go to 10.6, I know that this has to be more than 10.6. Now, what is the voltage required at this point? Now, if we calculate if this is 10.6 and that is across 10K, then what is the voltage across the other resistance? Now, we can go to the next page and see. So, essentially if I draw only that short circuit part alone, that circuit looks like this, and I have that goes to collector, and that goes here, and that is connected here. So, this is 10 volt, and this has to come to 10.6, and we have said this is 10K and this is 0.5 K we have taken. So, what is the voltage required at this point to get 10.6? So, the voltage across this if I take, that is 10.6. So, you have 10.6 divided by 10K into 10.5 K, that is the voltage, that is Vx, that is Vx. So, if you calculate this, that comes 10.6 into 10.5 divided by 10. So, if you calculate this, you will end up in having for example, this 10.6 into this division, if you remove 1.05 will be coming. That will make this will this go to I can multiply this. So, you can see if you multiply this, you will end up in getting so you get zeros here, and you will soon find okay, that actually you will find that there is something wrong here. 10.6 into 1.05 105. So, you get 33 6, you get, I had to move this out, there is a mistake here, to move this out. So, you will get 5 and get 6. So, you get okay, I remove this again. So, you will have this is 501. So, that comes 3 1 1 1. So, you will have 11.1 volt supposed to come here. That essentially means this will be equal to 11.1 volt. That means only when 11.1 comes, you will get 10.6. Now, you find that difference between these 2 points for short circuit condition, the difference between these 2 points is 1.1 volt. In the earlier case, it was only 0.7 volt. Now, you need 1.1 volt. That means, if I had taken 1 ohm resistance, in our example, we had taken 1 ohm and then current limiting short circuit condition took place at 0.7 ampere. Now, if I take the same 1 ohm here, then to get 1.1 volt difference, because this is 10 and this is 11.1, to get the difference of V difference of 1.1 volt, I need current of 1.1 amps. That means, on a normal condition, it limits the current at 1.1 ampere. Under short circuit condition, it limits the current at 0.7 amps. That is what we had seen in the earlier example, earlier workout. So, that means, under short circuit condition, we can limit at much lower current than what is available under normal working condition. Now, this is possible because because of this voltage division. If I keep this resistance larger, then even I can make this ratio much larger. For example, I can make it 1:half by selecting this resistance suitably, that you can work out and see how to select for different amount of current. So, essentially by selecting these two resistance, one can get different current for short circuit and different current for normal working. This is very important. If you do that, then one can limit the current at whatever rate that is required, whatever current that is required for short circuit and whatever is the normal current that is required for normal working. So, this is about foldback current limiting. You work out for different resistance, you will get the idea of how to reduce the current under short circuit condition. But actually, the basic principle of working is like this: the voltage that is there across this resistor, voltage across there this resistor under normal working, because a normal working condition you have 10 volt and that 10 volt also will be reflected here. That 10 volt is divided between these two resistors. So, there is some voltage drop across this under normal working condition, that is working as a reverse bias for this, because this is 10 and if this is in the normal, for example, if there is no current, if there is no current, and this is not going to be 10, because if this is a normal current, if there is no current, if this is 10, this is also 10, and this is not going to be 10, this is going to be around 9.5 volt, voltage at this point going to be 9.5, this is 10. That means this is 9.5, this is 10, means this is already reverse biased. So, voltage across this transistor, if you take the voltage across this transistor in the normal working condition applies a reverse voltage. So, under short circuit condition there is the voltage across this is very small, because the 10 volt had disappeared and here also it had disappeared. So, there is no voltage across this under short circuit condition due to this 10 volt. In the net result is, under normal working condition you have this transistor reverse biased, and that reverse bias disappears moment you short circuit. So, it limits at much lower current. That is the crux of the issue if you forget about the mathematics behind this, because if you mathematically remember, it is very difficult to design the circuit. So, if you remember as a reverse bias and follow this example, it will be very clear that fallback current limiting works depending upon depending upon the voltage across this. So, one can alter these two resistance to get the required short circuit current. So, this is about short circuit protection given to the voltage regulator. Now, we had made a long journey in the voltage regulator, because our idea was how to use the operation amplifier as a error amplifier in the voltage regulator. Now, these things are available as a 3-pin regulators available in the market today, which has all built in protection what I had discussed so far. That is, for example, all that user does is that you can have the suitable transformer, which I had discussed how to select. So, you have the rectifier and then have the suitable capacitor. I told you how to override the transformer and how to select this capacitor. All that you do is you put this regulator here, and that regulator, for example, I connect this to ground, for example 7815 is there, then you will get output voltage at this point 15 volt, and this unit as the short circuit protection what I had discussed. Some of them have fold back, some of them have a simple short circuit protection, and some of them have short circuit protection plus sensing the temperature and shutting down all that. Of course, the heat sink to be designed as I discussed in the circuit, and the transformer also be designed as I discussed. Maybe you will save on this operation amplifier and the circuit that went along with that in the regulation, that is already built in this. Of course, the what discussion that we had regarding how to design a voltage regulator will be useful at very many places, even though you are not using that type of regulators right now. For example, you want to use a high voltage regulator, then one must have a circuit which I discussed earlier. For example, if you want to make 100 volt regulator supply, then you won't be getting this 7815 regulator for 100 volt. In that case, we had to design a new circuit that actually goes like this. For example, the existing whatever the circuit we have discussed will not work for 100 volt, because the op amp cannot give more than 15, because if I see the circuit which we have discussed so far, for example, if we take this voltage at this point has to be more than the output voltage. Suppose if you want output 15 volt, then I know this can go up to 15.6 like that, and this has to go to 16.2 and 16.8, this has to go to 16. If you want 100 volt here, then this has to go to 100 volt or more than 100 volt, and that means this has to be more than 100 volt, and you will not get op amp for 100 volt. So, this circuit will not be useful for high voltage application. Of course, this can be slightly modified to make it work for high voltage, and that modification I can show to you now. So, what you can do is for high voltage we can change the configuration like this. You have the transformer and have the rectifier. Of course, the transformer has to be of now if you want high 100 volt, then we need to have at least 140 150 volt depending upon up to what voltage, what input voltage you have to get 100 volt output. Depending on that you can select. That discussion is same as what we had discussed earlier. So, I put here the rectifier and filter arrangement, and then a similar arrangement I give what we have discussed so far, that with the series pass transistor and one Darlington to boost the current. This is similar to what we have discussed so far. Then output also you have, if you want you can provide a short circuit protection, because short circuit protection is a must in all cases. So, we will give a simple short circuit protection here, whether high voltage or low voltage that remains same. So, I will put a short circuit protection and connect to the base. Then you get output. The output again I have to put a capacitor to avoid oscillations. This we discuss little later. Now, I will take the output and same way I will also give a feedback by take the part of the output and then give it to the operational amplifier. Here is the change. We give now to plus input this, and then to the minus input I give the reference Z0. Then supply for this op amp cannot come from this 100 volt, because op amp cannot take 100 volt supply. So, I put one more rectifier and filter, and this ground is same as this ground, but only thing is this is a this is only a small voltage 15 volt secondary, this is 100 volt secondary. So, you will get 15 to 20 volt only at this point, not high voltage. This voltage I can give it to operational amplifier supply. So, I give this to the operational amplifier supply. So, operational amplifier now gets its required, because you cannot give 100 volt to this. Now, what I do, I will connect this fellow, the output. Suppose if I connect directly to the output like what we had done earlier, it will not work, because this supply voltage what we have is only 20 volt, and this cannot go more than 20, in the sense that if the supply is 20, then this cannot go more than 20. So, if I connect this here, then this output can go only 20, not more than 20. Because if this itself 20, then you have to have 20 here and 19.4 here and 18.8 only maximum possible, but we want 100 volt. So, we cannot connect this directly to get high voltage output here. Now, what we do is we want high voltage. So, what I can do is I do not give this directly to the output, I give it to for example, I can have a transistor arrangement here, then connect this to the collector and put this transistor here, resistance here. Now, this works as a high voltage regulator. What you have done is, instead of connecting the output to the base of this transistor, we have connected this output through this transistor and this resistance arrangement, such that you will get high voltage at this point, and that is transmitted here. Of course, if the voltage goes high, then this goes high, then this will go high, and then if it goes high, then the current will flow more, and this current also will flow more. So, more current flowing here will reduce the voltage at this point, that will reduce the voltage at this point. That is how it regulates. So, if the suppose the voltage goes too low at this point, then this is low, this is high. So, output goes to 0, because the minus is higher. It is supposed to go minus, we have no minus supply. So, output goes to 0, and if it goes to 0, then no current flows through this, then no current flows through this. If no current is flowing through this, there will not be any voltage drop across this. If there is no voltage drop, then this voltage goes high and then output goes high. So, essentially if the voltage goes high, then immediately this conducts more and brings down this voltage and output comes down. If the output goes too low, then this goes high and then this goes low and then less conduction and less conduction here, and this voltage goes high and output goes high. That is how it regulates. So, the regulation is similar to what we had discussed. Only thing is we had a new comments that is this that is this resistance, this transistor and this resistor come extra, so that you are able to regulate at get high voltage. What really happening is this is acting as a another amplifier to amplify the voltage. For example, if this voltage increases, essentially more current flows through this and then more current through this, and the voltage at this point comes down. Similarly, if the voltage comes down here, automatically the voltage increases here. Of course, we can by varying a small voltage, we are able to vary large voltage here. For example, if the resistance I put here is 10K, then when 1 milliampere current flows through this, you will have a 10 volt drop. If that means whatever voltage is here, say 150 is there, then 10 gone here means you will get 140 here. If you want to bring down to 100 here, then I had sent 5 milliampere current. If this, for example, if this point is 150 and if I want to bring this one to 100, then 5 milliampere current have to go through this. For that 5 milliampere, this voltage have to increase. That is what it is doing. A small increase in voltage will increase the current here, and that will increase the current here, and that will reduce the voltage. So, small change can bring a large change at this point, and that is what happening. Then that also changes here, and you will able to get change here. So, anyway, if voltage at this point is kept at 5, and this also will remain at 5 only. Actually, the difference, it will not be exactly 5, it will be this has to be positive. So, it will go little more than 5. So, for example, to make this to conduct, if I put, for example, I put here 1K and 1K, I know this has to come to 0.6, this has to be around 1.2. If it has to be 1.2, then the difference required is 1.2 divided by open loop gain, because if I want 1.2 divided by open loop gain, which is very high, say 20,000, then I need only about 0.1 millivolt difference. So, this goes roughly 5.0001. So, it goes little higher, and that rise, if the voltage goes little more, then more voltage will come here, and it will conduct more current and more current here, and it reduces this voltage, and output also comes down. So, eventually if I set this one, if I keep this one at 5 volt, this will also come to 5 volt, and according to the ratio of these two resistors, the output is determined. For example, if I want 100 volt, then what I do is, if I take here 1K and if I put 19K here, then I know across this 5 volt, across this 95 volt, because 1K is 5 volt means 19K or 95. So, 5 plus 95 will give me at this point 100 volt. So, you will have 5 volt here. So, 5 volt across this, and then you will have 95 volt across this, and you will get 100 volt at this point. So, you can similar to the earlier case, you can vary this resistance and get a variable voltage at this point. This is how the high voltage electric works. The short circuit protection is controlled by this. This is same as what we had discussed earlier. You can also provide a foldback and limiting even to this. So, for that what you do, same thing, you remove this, then put the voltage divider arrangement here and connect this fellow here, then it gives you foldback current limiting that we had discussed earlier. So, this is a configuration for high voltage, and of course, there are few other configurations also can be used for high voltage regulation, and this is one of them. For example, I can modify this and get a different circuit for high voltage. I show you one such modification. What you do is, even I can get high voltage, I remove this fellow, this circuit. Now I can do one thing, I can put on NPN transistor here, put one resistance here, connect the collector here, then connect this. Of course, I have to connect the transistor here. The same circuit, connect this. This also works well. This also gives you the high voltage regulation. What we have done is, we have removed that this resistor was directly connected. Now we are connected through a PNP transistor. This has several advantage over the previous circuit, because if this voltage if voltage at this point goes up, then more current goes here, then more current goes through this. The more current will produce a more voltage drop across this, and that will put a more voltage at this point, because that once voltage across this goes more than 0.6, this will be start conducting. So essentially, if this voltage increases, then you will have increased current through this, because this base current is increasing, that will increase the collector current here. That collector current eventually comes from here. So essentially, you will have more voltage current flowing here, produce a more voltage drop. If the voltage across this goes more than 0.6, then you have more voltage at this point. So increase in voltage increases this voltage and increases that voltage at this point. If that means that increase the voltage here, that will increase here, and then that will increase this and further increase this. So it will go into positive feedback. So if I use this circuit, all that I do is, I will change this, instead of minus, I put plus minus there and then put plus here. So now if the voltage goes up here, if voltage at this point goes up, then this voltage also goes up. That will make this to decrease. The decrease in voltage will decrease this current, that will decrease this current. So that if the voltage decreases here, the voltage across this also decreases. That means you have reduced the base emitter voltage of this. The base emitter voltage decreases, obviously this voltage will decrease, and then this voltage also will decrease. So that is how it acting as a negative feedback. So if you set at 5 here, this also eventually will come at 5, and depending upon this resistance ratio, you will get your output voltage. So you can also have this kind of configuration for voltage regulator. Of course, you will soon find that it is useful if I put on small series resistance here and do it rather than doing it. For example, I can modify this circuit further to get a much better regulation. Like I can have this, I can put one resistance here and ground it and connect this, connect this. In fact, this circuit works much better, because if the increase in voltage will increase the current here, that will increase this voltage. So this voltage across this acts as a negative feedback. So the gain is controlled tightly, because if small increase, if increase the current here, that will increase the voltage enormously here, and this voltage cannot go more than 0.6. So to control the gain, we can add a emitter resistance and make it work, and it works in a controlled fashion. So this circuit also works nicely for high voltage application. In fact, this is better than other two circuits. The reason for that you can see, because in this case, if the power supply for this is not reached first, for example, if the power supply for this not reached first, then this voltage won't be there. If this voltage is not there, no conduction will take place. If no conduction is there, no conduction, no voltage drop across this. That will make 0 volt appear here and 0 volt here. That means unless the power supply arrives at this, there won't be any output voltage. This is not the case in the other circuit, which you can see quickly. For example, if you see the earlier circuit, our high voltage circuit, what we had seen. Okay, I think we have removed that. For example, in the high voltage circuit of other circuit, that is without this, for example, our old circuit, we had put this resistance directly here and then connected this here, and then we had modified this, this was we had this as plus and this as minus. In this circuit, if the supply for this comes late compared to this, that is, if this supply comes first and this supply comes late, then you will find that when there is no voltage here, 0 here, then no conduction takes place here, and this voltage will be high. That is because there is no current, this voltage will be high and output will go high. That means initially you will get a high voltage output, and then it will settle to the regulated voltage in this case, whereas the second circuit what I had shown, that problem is not there. So, the spike problem is avoided by adding one more transistor there, which I had shown earlier. So, this is how this is what we had seen the voltage regulator circuit, that is for low voltage out, how to use this, how to connect the circuit, that is how to connect the op amp, and for high voltage how to connect the op amp and the transistor, and then also discussed about the current limiting, both normal current limiting and the foldback current limiting. Then I also discussed about the heat sink design and the transformer design. This completes the complete design of voltage regulator. I think you might be understood now that voltage regulator itself has lot of things that has to be learned, like how to design a transformer, how to design a heat sink, how to design a closed loop, then how to avoid the spike, and so on. Many things we have learned, and we will use these concepts in the coming weeks, in the coming lectures for the in the analog circuit design course. We will see in the next week. Thank you.